Hi everybody. So this lesson 2.3 is the first of three lessons where we're going to talk about different items to consider when factoring. So before we get into factoring, I just have this first slide where I want to go back to basics and talk about what an algebraic expression is, because factoring is going to involve combining of multiple algebraic expressions. Okay? So an algebraic expression has one or more variables, and usually they're combined with numbers and mathematical operators, that being, add addition, typically addition and subtraction. Okay? An expression may have a single term, or it may have multiple terms that are added and subtracted together. So in this case, this is all one expression. It's 3n plus 5. Okay? So in this expression, there's two terms, 3n and 5. Okay? So a term can either have, a number and a letter, or a number and a term or function like n multiplied together. It could just be a number, or it could be something like x squared or x squared y. Okay? That all of those are known as terms. Okay? Constants are a term or the item in your function that does not have a variable. Okay? So in this case, the number 5, you'll look back to this, is a constant. Factors are values that are multiplied together. Okay? So 3n has two factors, the number 3 and the function or variable n. Okay? The last item to talk about in a function is a coefficient. So if you go back to 3n, okay, the coefficient of it is the number that's sitting behind that variable n. So the coefficient in the term 3n would therefore be 3. Okay, so those are just some basics to keep together, just some lingo, before we start talking about how to manipulate these functions and combine them together. So when you look at an expression, the first thing to note is adding and subtracting them. They can only be added and subtracted if they have the same variables. So in this case, we have 2x minus 6xy. You can't add those together, right? This does not become negative 4xy, okay, or negative 4x. You can't add them together because they don't have all of the same terms. This one has an x, and this one has an x and a y. Okay. Similarly, you can't add, say, 2x plus x squared, because this one has an x term and this one has an x squared. Okay. But what you can do is you can what's called factor out the common pieces between them. Okay. So in going back to 2x minus 6y, okay, I'll erase these arrows and we'll start from scratch. If you have 2x minus 6y, they both have an x term. But what you can also see is one has the number 2 and one has a 6. Well, remember back to when something's a multiple or of a number or a factor. 6 is the same as 3 times 2. Okay? The other way you can think of it is 2 or 6 is a multiple of 2. You can have 2, 4, 6, 8. Okay? All multiples of 2. So you can pull both those numbers out and then multiply it by your resulting expression. Okay? So in other words, let's start with 2x minus 6y. The first term that we all saw was that they both have x. So you can now what's called factor x out or move x outside of this equation and then place brackets there and you remove the x from both functions. The reason you can do that is if you have an expression like this, when you multiply this out, what you do is you multiply the x by both variables here. So if you were to write this out, you'd have x times 2, which is 2x, minus x times negative 6y, which is 6xy. So you end up with the same thing you had previously. You've just factored out that variable. Similarly, okay, now that you have this function, you can also factor out constants. So like I said, 6 is a multiple of 2, right? So if you remove 2 out of this equation and multiply it into these, Okay? What you're left with is just 1 minus 3y, because you've pulled everything you can out of this piece, all the whole 2x. And with this one, the only thing you're left with is 3y. And again, you can check that by then multiplying it in. This is what's called the distributive law. So 2x times 1 is 2x, minus 2x times 3y becomes 6xy. So you always end up back with what you started with. Okay, so factoring allows you to find multiple little factors. And when we talk about quadratic equations, you're going to see why this is an important piece of the puzzle. So I want to just explain this to you with several examples. Okay, so we saw one in the last slide, but you basically factor these until you can no longer pull something out of them, okay, to multiply it out. So first question is factor the expression 3xy minus 12xzy minus 18x. So the first thing you see here, I see an x, an x, and an x. So my first thing I know I can take from all of them is x. So if I do that, I have x, and if I remove it from each, I'm left with 3y minus 12zy minus 18. Okay? So you can do this in steps, or you can do it all in one shot. Okay, it's totally up to you. Next I look, there's a y here, but no y here. So you can't factor y out. There's just a z in this term, meaning you can't factor the z out. But you can see you have a 3, a 12, and an 18. 12 and 18 are multiples of 3. So I know I can take 3 or factor 3 out of this equation, okay? And if I do that, I have 3 times x. Then I remove the 3 out of here, so this is just y minus. So what you do is you take that original number divided by 3. So 12 divided by 3 is 4, zy, minus 18 divided by 3 is simply 6. So now I have nothing left that's in all three of them that I can factor out, okay? I can't factor the y out. 4 and 6 are both multiples of 2, but this one doesn't have a 2, right? So I can't factor that out, all right? So there's no more steps I could take in order to factor this any further, okay? So factoring is just doing it in a series of steps, okay? So let's look at a second example. 3a minus 3ab plus 6bac, okay? So it's asking us to factor this expression. Again, the first thing I note, I always start with the variables or the letters, the a's, x's, y's. They're the easiest to visualize, and then I start to look at the numbers to see if I can factor individual numbers out. So I see an a in all three, so I know at a starting point I can factor out a. So this equals a, and then you by removing it from each of them, right? The easiest way I think about it is you divide each of these functions by a. So you're left with just 3 minus 3b plus 6b times c. So now you look at this and you think, I can't factor out the b and I can't factor out the c because they're not in all three expressions. But I do see a number 3 here. There's a 3 in this expression and this expression. And I know that 6 is a multiple of 3 because 3 times 2 equals 6. So I can then factor out a 3. So I have 3 times a, and now this is multiplied by, if you're dividing, again, if you want to think of it this way, dividing each of them by 3, we're left with 1 minus just b, because 3 divided by 3 is 1, and 6 divided by 3 is 2. So we're left with plus 2 times bc. Okay? And now you see here, none of the numbers can be factored, and none of the letters can be factored out because they're not in every function. So that means, therefore, our final answer is 3a times 1 minus b plus 2bc. Okay? You'll see this is a general factoring version where I'm going to show you where this factoring really comes into play when we start getting into trinomials as well as factoring the quadratic equations. So the next thing I want to talk about is factoring by grouping. Okay, so you saw that in the last examples, each of those examples might have only had, by the time you were done factoring, there were two terms that might have had something like the letter B, but the third term did not. And you might run into instances where you've got 4 or 5 or 6 terms in an equation, and you can group them into individual groups that you can factor individually, and then you can figure out that might lead to an even more simplified answer. It doesn't always happen that way, but there are some instances where it does. So let's look, for example here, if we have 2x plus ax minus 2y minus ay, okay? You can factor these by grouping, and by grouping I mean both of the variables with a 2 as the coefficient. You can group them together to become 2x minus 2y. And the two variables that both have an a as their coefficient, okay, can be grouped together into ax minus ay. And then you can see that they have something in common. Each of them have a different item in common. So you can factor them separately. 2x minus 2y, we can remove 2 from both functions. So we're left with 2 times x minus y. Then we have plus, and the next two functions, we can remove the a and factor it. So we have a times x minus y. Well, now you see we've got two terms that are multiplied. We have 2 times x minus y plus a times x minus y. Okay? Well, it doesn't have to necessarily have every term multiplied together. Both of these terms now have x minus y. So you can factor the x minus y piece out. Okay? See how they both have it. And if you do that, you're left with x minus y multiplied by what's left, right? Remember, when you're factoring out, you're dividing these by x minus y. Okay, so if you do that, the x minus y's cancel on both of them, right? Because you factored them out. And you're left with just 2 in the first expression and a in the second one. So it becomes x minus y times 2 plus a. This type of form is the form that you're going to see most often for factoring when we talk about trinomials, okay, which is the third of our factoring lessons, and then in our next unit when we talk about quadratics, okay? So with that, let's look at a few examples. So factor the expression 3ax plus 4xy minus 2x plus 3ay. So I'm going to follow the same method that I did in the previous slide. I see a term with a 3a and a 3a, and I see a term here with an x and an x. Okay? I'm going to rewrite this. Again, you can move all these around as long as you carry this sign of the function with it. Okay? So if I rearrange it, I have 3ax plus 3ay, and then plus 4xy minus 2x. All I did was rearrange. So in the first two, I'm going to factor out the 3 and the a. So we're left with 3a times x plus y, right? All I'm doing is removing the 3a's from them. And in the second one, I have an x, but I also see that I have a 4 here and a 2 here. And remember, 4 is 2 times 2. So it's a multiple of 2, meaning I can factor out a 2 and an x here. And if I do that, I'm left with, if I remove 2x from this, I'm left with just 2y. And if I remove 2x from here, I'm left with just 1 because I've got nothing else left, right? I've factored out everything. Okay? Now in the previous example, you saw that the item in brackets was the same, so you could factor it further. It doesn't always happen that way. Okay? Sometimes this is the final factoring, and that's entirely okay. I want you to get used to not necessarily always getting what is a really comfortable and really neat and tidy answer, okay? It just, when you talk about this in real math terms, it doesn't happen very often. So since I can't factor any more here, this therefore is my final factored answer. Okay? Okay, so our second example is factor the expression 3x minus 3a plus 2bx minus 2ba. So I see two terms here. This one has a 3 behind both. And this one I see has a 2b. Okay? So I'm going to keep them kind of in their groupings. I don't have to rearrange. So I have 3x minus 3a plus 2bx minus 2ba. So in the first grouping of 2, I'm going to factor out the 3. So I'm left with 3 times x minus a. And in the second grouping, I'm going to factor out both the 2 and the b, since they're in both terms. And if I do that, my first term, I'm left with just x. Okay, I'll show you that in a different color. And the second term, I'm left with just a. Okay, so in this case, I have now x minus a in both terms, just like you saw in my first example before we did a practice problem. So I can then remove the x minus a from both terms and factor it out. So I'm left with x minus a, and by removing that from both terms, I just have a bracket now. In the first term, I just have a 3, and the second term, I have a 2b. Okay, so this is what I refer to as the neat and tidy solution. Okay, multiple terms multiplied together, so you're left with these kind of neat and tidy sets of brackets. Again, it doesn't happen in every instance, okay? But when it does, you'll see why this is important when we start to talk about quadratics. So our last topic in this lesson, you'll see that this is a shorter lesson. The next 3 will all be shorter ones, but will require you to do a lot of practice exercises, okay? Factoring starts to come a lot easier to you and start to be a lot simpler as you practice, okay? It's not necessarily something you grasp by initially just looking at it. Yes, I can factor. I know that 2 and 6 is a multiple of 2, okay? Items like that. So again, shorter lessons, more practice. So our last topic is difference of squares. And this is when you have 2 items or 2 terms that are squared, okay? Or the square of a number, okay? Another example could be that you have a term that's 9. So 9 is actually 3 squared. And when I say difference, it's because one is subtracted from the other, okay? Period. That's what it means when it says difference of squares. Okay, so kind of thinking of it that way. And when you do, there's a simple kind of answer to how they work out. If you have 2 terms that are both squared, subtracted from one another, that's the same as writing it again in one of these neat little packets of x plus y and x minus y. In other words, if you have an example here, r squared minus 25, okay, well you know that 25 is equal to the square root, or is equal to 5 squared, okay? In other words, 5 is the square root of 25. Remember when we talked about radicals. So knowing that, that's the same as writing r squared minus 5 squared. Okay? So if you do that, you just take the term that's being squared, and you have, so in this case, you have r plus 5 and r minus 5. It's as simple as that. Every time you see an expression like this, you can simply write it in that form there. Okay? And it applies even if you have a coefficient behind it, okay? So if you have 4y squared minus 81, remember, 4 is equal to 2 squared. So this is the same as 2 squared times y squared minus 81, okay? In this case, 81 is equal to 9 squared, right? Because 9 squared is 81. So this is the same as writing 2 squared times y squared minus 9 squared. So they're all squared terms, right? Separated by a minus sign. So you can write them as 2y plus 9 and 2y minus 9. Okay, it's as simple as that. So let's look at one more example. We had 2 in the last one, then we'll look at this one. Factor the expression 9a to the 4 minus 16. Again, okay, 9 is the same as 3 squared. A to the 4th, remember back to our rules of exponents. A to the 4th is equal to a squared squared. Remember our rule for exponents. A to the exponent m raised to the n is equal to a to the exponent m times n. Okay, so when you have something as an exponent raised to another exponent, it's the same as multiplying those exponents together. Okay, so looking on the first two, we can see that they're different functions that are squared. And 16 is the same as 4 squared. Okay, so again, this is why I talk about practice. I don't expect you to look at this. I expect you to look at this example and say, where did he get that from? How am I possibly supposed to know those squares? And the real reason is practice. That's the only way that you're going to be able to see these quicker. So knowing that these are all squared functions, I'm going to rewrite them. Okay, so we end up with 3 squared times a squared squared minus 4 squared. So you can see they're all squared. And remember, when you have two terms like that that are both squared, how we can technically write this is we can write this as 3a squared, all squared, minus 4 squared. Okay, again, going back to our rules of exponents. And if we do that, again, because now they're being subtracted, they're both functions squared, we can apply difference of squares. So I'm going to put my two sets of brackets here. One is a plus, one is a minus. And now we just fill them in. So this first term, 3a squared. And the second term of 4. So we're left with 3a squared plus 4 and 3a squared minus 4. Okay? So that is the premise behind the difference of squares. So this was a short lesson. Okay? What I encourage you, though, is to look at the exercises. This is from exercise 6.2. So in other words, chapter 6, section 2. And I've shown numbers 5 to 46. And I say odd numbered problems only because most of those have solutions in the back of your textbook. All right? You can do all of them from 5 to 46 if you choose to, but some of them you might not necessarily have full solutions for. So if you have any questions, please send me an email or attend one of our tutorial or drop-in sessions. Thanks, everybody.